시작해보겠습니다. Last time we talked about dynamic system for two legs connected together like this, and we developed mass balance equation for number 1 and number 2 by counting incoming errors and outgoing errors, and we developed those two. And we simplified the equation for steady state case, which is 0 here and there, and we can apply matrix analysis or linear algebra to calculate C1 and C2. So one of the method that we can use is Cramer's rule. Obviously, we have many other methods to solve this kind of stuff. And that Cramer's rule also can be used to solve 3x3 matrix like this. But if this augmentation matrix is becoming large and large, and that Cramer's rule is going to be more and more difficult to apply because you have to multiply those questions many times. So to reduce that kind of work, we can use other methods like this. We can talk about that in our next chapter. Also, we talked about time variable solution for C1 and C2 by playing with two equations, and we can equally simplify the equation for C1 and also C2, and these equations can be solved by using second order polynomial method. So you did, okay? And this is very similar system, and this one is actually let's have a look at our textbook 6.5.1. Right? And if you take a look at page 114, and we have system like this, and you have in your water tank, you have A and B, those are reacting together, and the rate or velocity of becoming A to B is KAB, and the rate that is becoming from B to A is KBA. So if you want to model this one, and because this whole system can be weak, so we can talk about dt, and what is coming in? What is coming in is K, BA, CB, V is coming in. What is going out is K, AB, CA, and V. So this is the mass balance equation for CA, and for DCB dt, and we have exactly the same equation but with opposite sign. So for B, this is going out, so KBA, CBV is going out, and then, right. Going out, right? Going out means minus, right? Okay. And then, and for B, KAB, CAV is coming in. So inside this reactor, let's say your C total is CA plus CB. This is constant, no matter what happens, right? And this is inside the, let's say you have 2 people in your apartment, okay? Let's say you have 10 people in your apartment, 10. So 2 people went to the living room, and 3 people went to the kitchen. But no matter where they go, always in your apartment, always there's 10 people. 10 people. Okay? Some people can be in the restroom, kitchen, living room, bigger room, bedroom, whatever. But the total number must be constant there. In this case, since they are in the same tank, even though sum of A can become B, and sum of B can become A plus B always have to be the same. That's mathematics, right? Okay. All right. So in other words, if you have dCt dt, this which is the differentiation of constant, this must be 0, right? Okay, then what is this? Then dCt dt equals dCa dt plus dCb dt. This must be 0, right? And if you multiply V in everywhere, you will have the same relationship. In other words, if you multiply these two, what we will get? We will get like this, right? So let's see if addition of these two equals, it will give you a 0. Plus and minus, minus and plus, right? Okay? Simple. And even though our water-cooled system, if you want to make a model for your river, for your lake, and situation may be very complicated, and in reality, yes, it is complicated, but the basic principle there is very much simple and clear. Okay, so what you have to look at all the time is you have to think about basic principle. And in real world, we may have some errors in measurement. Okay, we can have a few percent error for measurement of A, few percent error for measurement of B. So there will be some errors in there. So if you make the experiment, if you make the measurement, that cannot be sometimes 0, but that's just error. But the science itself, or the exact mathematics behind, must be like this. Okay. So you have to always follow the basic rules. That's very important. Okay. So in here, and if I divide everything by my V over there, then you can have the relationship for CA and CB. Okay. Now at steady state, okay, and let's see. In this case, we will practice how do we play with this kind of relationship. Okay, at steady state, okay, if at steady state this one is 0 and this one is 0, and so KABCA, which is multiplication, these two will be the same as KBAC. And yeah, KAB, right? Okay, and these two are the same. Okay, so I will just define the ratio of CA and CD is like K. This is something like equilibrium constant when you study your chemistry. Okay, so once we have this kind of relationship, we can say that okay, since my the ratio between CA and CD can be like that all the time, then my CB is KCA. But in reality, this may not be constant. In this case, we're just assuming this is constant. Okay? So don't be scared. It's okay. So, but in the real world, always we have some variable uncertainty. But anyway, so if CT is sorry about the capital letter here, and those are the same. Anyway, so this one can be written like that, and 1 plus K CA is CT. In this case, we could simplify the equation by reducing number of variables. Because we have two unknowns, CA and CB. Now we have just only one CA. So we can also decrease our headache as well. Okay? So this is like that. So simple, very much simple. And then we want to kind of calculate the fraction of CA and CB. Okay, let's say that my CT is 1 plus KCA. In other words, my CA is 1 plus K CT. Then what is CB then? This must be like that, so that if we add them together, then must be CT, right? So your denominator and numerator should be the same. Okay. So what is this? This is kind of fraction or percent if you want to use that one, and if you times 100 is percent, or itself is a kind of a ratio. Ratio for CA is this much, right? And obviously, 1 plus K1 and 1 plus K, that should be less than 1 and must be greater than 0. Because we know addition of those two is 1, right? So, and if K is 0, then if K is 0, everything is CA. At that time, your CB is just 0, okay? And if your K is too much, too big, and then the reverse situation is going to happen. All right. So in this case, I can also express, if I want to say this one is your F, then this is F CT, right? FA CT. And as you can see, this one is 1 minus FA CT. Right? This, in other words, this is F would be CT. Right? So always FA, which is 1 plus K, and plus FB, which is 1 plus K, that should be the same as well. Okay? So first, very much simple, and then I can also use my mass balance equation to solve K, A, B, C. I think this was K, B, A, C, B minus K, A, B, C, A, right? And then I can put the equation back into my system. And let's see. Because I know the CT is CA plus CB, and my CB is, let's say let's just use C, because C in this case C equals CT plus whatever. Okay, then C minus CA, and then we can use the information into here and to solve everything for CA. this case, we only have CA as unknown. So we have practiced how to solve this kind of equation before, so we can solve it. All right. And so this one shows, so far, we have talked about the system that doesn't have any input and output, which is just a little fish tank. But if we have information that something is coming in and something is going out, then we can add those information for CA, and this is input and this is output, and those are reactions. Something coming in, something is transforming, something is generating, and something is decaying. So we can use those information. So for same story for CB, and by the way, what is going on? What is this? This one, well, I think this one is if you know CB is reacting in a certain if you have information, let's read our textbook. Let's go to page 116, right? And in the third row, in 6.5.2 of an open system, it says, in addition, assume that B is also subject to an additional reaction that removes it from the system. And if we have an additional system that can be removed from the system, then we can add that factor here. Okay? So then we can simplify the situation, and if we can add them together, if we add them together, we can simplify this equation like this. Okay? We can add it together and then solve system using the equation. Okay, so I'm done for 6.5.6, chapter 6. And we will talk about that, some other stuff, but and I will just, it's going to be better when we really have the situation. We're better to talk about those when we have the situation. Well, numerical integration. And let me see if I have more. Okay, we'll talk about those later, but in here we will talk about cascades. Cascade is like your waterfall. Okay, this is like a small waterfall is a cascade, and in next figure. And this one is the, if you assume this is the river, okay? Let's assume your river can be divided into many different parts. In here, we know something is coming in, which is W1, there can be loading from somewhere, and QC0 can be the information from your upper stream area. And something is going to go out, and this is QC1, and decay can happen in there, and in between we have some dispersion. If you go to second row, I want you to try to understand every term in here. Okay, in here, let's bring up a little pen. And then I know something is coming in, right? And decay and dispersion, right? So I have something coming in directly from somewhere in the area. So how many terms do I have? I have actually 1, 2, 3, 4, 5, 6. And do I have 6 terms? 1, 2, 3, 4, 5, 6. Right? Okay. So this is coming in, it must be plus. Another coming in must be plus, which is the outflow of this one. And this one must be outflow for the second segment. And KCV is the decay. And this term is between C1 and C2. And we have not talked about this dispersion number. Actually, this one is called a Burke dispersion number, which has the unit of Q, because we always have to have same unit and in the same linear equation. Anyway, then this one is representing this part, and this one is representing this part. So now you have 6 arrows. Actually, what this one is can be regarded as like this, just like let's see. One. Okay, and let's just forget about this. Okay, in here, let me use some other color. Okay. And through dispersion, something can come in. Also, we can say something can go out. Something can go out, and something can come in. In this case, how many arrows do we have? We have now 7. No. 1, 2, 3, 4, 5, 6, 7, 8. Right? 8 arrows. We had 6 before. 8 arrows. But actually, let's take a look at this. 1, 2, 3, 4, 5, 6, 7, 8. Actually, we have 8. Right? 8 terms. Well, and then we just somehow collected those in parentheses, but it does not allow us to reduce the number of terms. Anyway, if we to be accurate, and we have 8 terms here. So what is E prime C1? That's coming in through dispersion. What is E1 C2? That's going out through dispersion. What is this? Something coming in from C3 to C2 through dispersion. Something is going out through dispersion. That's what it is, actually. Okay? Anyway, so if you can keep doing the same process for the next so many segments. But as you can see, if you multiply them together, you can have cancellation of this Q things all the time. So we can actually also, if you have a look at this and that, this one is the same term with the reverse sign. So you can cancel every E terms except the last part. Okay? The solution can become very simple. Then, so what you will be left with is in the first, okay, and in this first equation, if you want to solve this one, what in this case I have 2 unknowns here. Two unknowns are C1 and C2. So this first line, and you have 2 different 2 unknowns there. In this second line, what you don't know is C1, C2, and C3. You have 3 unknowns. And you have 3 unknowns all the way down, and then also in here, what you don't know is Cn plus n minus 1 and Cn. That's it. So first and last term you have 2 unknowns, but all the other terms you have 3 unknowns. So your equation is going to become like this. For steady state, steady state means you have your left hand side, all of your left hand side is going to become 0, right? Then your first row, you know you have C1 and C2, so you can rearrange our equation like this. And the next line was you have 3 unknowns, which was C1 and C2, C3, and then we can rearrange the equation. So all the way to n minus 1 row, and for the last row, and we will assume we have the boundary concentration that we don't know. Boundary concentration actually can be Cn plus 1. In this case, I will assume I know that. Okay? Even though most of the times I don't know, I will assume I know that. So that's the boundary concentration. You have to know at least some information, otherwise we cannot use all this equation. So if you rearrange this equation in the form of matrix equation, we can have this one. So this is which we call this as diagonal element. This is upper diagonal, this lower diagonal, and we have 3 terms. So we do call this a tri-diagonal matrix system. And to solve this kind of method is so-called TDMA, right? Tri-diagonal matrix. How to solve this equation that method is called as TDMA, and which is very simple. Okay, for the finite difference, finite means you have just a number that is you just can count the number. Okay, in this case, finite, you have just 9 segments. In here, I have more than 9, and you have so many different segments here, and which is 9 times 9 times 9, right? Okay, and then but anyway that you can count. And what is D? D is abbreviation of dimension. That also can be regarded as a direction. If you have 2 dimensions, that means you have 2 directions, right? And one direction is just X direction. So far, this kind of system is 1D. You just have only one direction, which is this direction. But if you have things like this and you have X direction and Y direction. So you have 2 dimensions, and which is you have 3 directions. In this case, you have X and Y and Z, right? So you have 3 directions, which that is 3 dimensions. Okay. So one direction is line, 2D is area, 3D is volume, right? And line usually is we talk about that's L or meter, A meter square, V meter cube, right? As long as you keep kind of order and consistency, you can solve your system for X direction only, and for X and Y direction, and then also for X and Y and Z as well. Okay, so this is your homework. Want to take a